This particular type of heat-sensitive seeker was developed for specific application to a contemporary guided missile, the details of which are highly classified. However, we will be able to look inside the missile's nose section, where the A-5 is installed as a completely automatic and sealed unit. The tip of the missile nose section is fitted with a dome-shaped window of silver chloride. This is only large enough to accommodate the angular coverage of the scanning mirror above it. The window material, transparent only to infrared energy, has been coated for protection against the deteriorating effects of sunlight and moisture. In operation, this seeker will automatically search for, detect, and lock on any suitable targets that radiate energy in the infrared spectrum. Immediately thereafter, it will continuously supply signal information for the automatic operation of the missile's control mechanism in such a manner as to effect a collision with the target. The component which detects infrared energy is the thermistor bolometer, mounted at the focal point of a parabolic mirror. The collecting surface of this mirror has a beam width of 1 degree. During target search, the mirror with its 1-degree beam describes a rapid spiral search pattern over a 20-degree field of view. In the laboratory's testing scope, the spiral search looks like this. The signal from the bolometer is amplified and processed to provide proportional control signals to the missile servo circuits. These control signals always correspond to the coordinate position of the target, relative to the longitudinal axis of the missile. When a target is detected through its infrared radiation, the signal through the bolometer activates circuits to the drive mechanism, which then limits the scan field to an annular region encompassing the target. Assuming that the target is displaced to the extent of 4 degrees from the missile axis, the scanner motion is limited to a spiral trace within 3 to 5 degrees from the center of the scan field, with the scanning mirror now intercepting the target every other revolution. On the scanning test scope, note the bright spot, indicating the target position. Such a change in interception rate amounts to an increase from the 1.2 coverage per second during the search phase to a rate of 4 to 10 per second during the final lock-on phase. The bolometer is subjected to a pulse of heat energy only while the scanner is on the target. When viewed on an oscilloscope, these pulses of energy can be evaluated. This heat energy is transposed to an electrical pulse which is used to activate those circuits which provide coordinate error output voltages for directional control of the missile. The amplifier, incorporating an automatic gain control, is biased to the level of the strongest signal. Lesser signals, due to thermal background conditions, are automatically filtered out by a peak signal selector, which allows only signals of a predetermined amplitude to pass. In operation, the A-5 target seeker unit is energized only after the guided missile in flight has entered into its period of terminal guidance. At this point, search begins at an altitude of approximately 30,000 feet. The seeker begins to scan the 20-degree search cone with its 1-degree beam, spirally scanning the entire field in less than a second. A target, in order to be detected, must be emitting at least enough energy to produce, at the altitude of the seeker, an energy level equal to 10 to the minus 8 watts per square centimeter. This energy must also be in the infrared region of the spectrum, within the wavelength region from 1 to 15 microns. Within the area scanned, there may be several possible targets or points from which heat energy is radiating in varying amounts. The amplifier and processing circuits will select the signal of greatest amplitude, which represents the hottest target. On the test oscilloscope, several signals of varying amplitude can be noted. Selection is made, and only the hottest one is retained. When the selected signal has been received, an electronic gate opens, and the target's position, with reference to the missile axis, is made available as voltages for controlling the missile toward the target. The opening of the gate also activates circuits which change the scanning from a 20-degree spiral search field to a 2-degree annular lock-on scan. In other words, the scan field during target lock-on is narrowed to an annular region, with variation in tilt angle of the mirror being maintained within such limits that the beam intercepts the target every other revolution. In this manner, lock-on provides target discrimination and correspondingly increases the rate at which target information is received. To avoid loss of target signal during lock-on, as may be caused by missile oscillation, a memory circuit has been incorporated to remember the scanner tilt angle when it last spotted the target. This retention of information, corrected with each interception, provides a target reference point about which the scanner spirals. Thus, upon loss of target, such as might occur through missile oscillation, the seeker continues to scan the same area until the target reappears, or after its memory time has lapsed, it will return to searching the complete 20-degree field. Target position relative to the axis of the missile is supplied in the form of DC voltages that are proportional to the error angle. In this lab test, target displacement is indicated by deflections of the meters. The meters are zeroed at the center, and the numerical scale shown has no significance. Relative position of the target within the scan field is indicated by the markings R, L, U, and D, corresponding to right, left, up, and down. Sensitivity tests under laboratory conditions, with the seeker mounted in a horizontal position, approximate the operation of the equipment under optimum conditions. With a uniform background temperature maintained, accurate measurements of seeker performance can be obtained.